We all like to think we're living in a pretty predictable kind of clockwork universe, right? Well, today we're going to toss a couple of scientific wrenches into those gears. We're going to dive into two really cool ideas that give us a new way to talk about the unpredictable. From the sudden snap of things we can actually see, all the way down to the fundamental maybiness of the tiny particles we can't.
I mean, we've all seen it happen. A perfectly calm conversation just erupts into a huge argument. A financial market that seems totally stable suddenly crashes. Or a quiet, gentle dog suddenly lunges. These moments, they feel like they come out of absolutely nowhere. Pure chaos.
But what if it isn't random? What if there's a hidden logic to these tipping points? That's really the first big question we're tackling. How can a system that's been changing smoothly, gradually, predictably, just suddenly leap into a totally different state?
So to get a handle on this, let's take a look at this classic example from the mathematician E.C. Zeeman. He was thinking about a dog's behavior. Now that behavior is being pulled in two directions by conflicting feelings, fear and rage. More rage and the dog gets aggressive, more fear and it wants to run. But what happens when both are high at the same time?
Well, the answer isn't just a simple 50-50 mix of the two. It turns out that conflict itself creates a situation where a sudden snap isn't just possible, it's mathematically predictable. This isn't just chaos. There's a beautiful hidden structure at play here.
And that structure has a name. It's called catastrophe theory. It was developed by René Thom as a way to describe exactly this, how gradually changing forces can cook up these sudden dramatic effects. It's like having a map for moments of sudden change.
Okay, so here's the crucial idea. When that dog is feeling high levels of both fear and rage, any kind of neutral, in-between behavior becomes the least likely thing to happen. The dog is now in what we call a bimodal state. It is overwhelmingly likely to choose one of two extremes, pure fight or pure flight. That middle ground, it's just gone.
And we can actually see this with the cusp catastrophe model. Just think of this flat bottom part as our control panel, our inputs, fear, and rage. And that folded surface sitting above it, that represents all the dog's possible behaviors, the output. And that fold right in the middle, yeah, that's where things get really interesting.
Let's trace two different paths on this map. First, let's say we only increase the dog's rage. See? Its behavior changes smoothly right along that top surface, from avoiding to growling. No surprises, nice and gradual. But now, let's try a different path. First, we crank up its fear, so it's down there, on the bottom sheet, in total flight mode. Then we start increasing its rage. It stays in flight mode, until it hits the edge of that fold, and then, bam! It catastrophically jumps all the way to the top surface, full-on fight mode. A smooth, gradual change in the inputs just caused a sudden, violent leap in behavior.
And what's so brilliant about this is that one simple shape shows us all 5 key features of these systems. You've got bimodality, the two stable states. You've got that inaccessible middle ground. You have the catastrophe, the jump itself. Hysteresis, which just means the path to get back down is different. And divergence, where tiny little differences in where you start can lead to wildly different outcomes.
Okay, so catastrophe theory gives us this amazing map for sudden changes in the world we can see. But what if this unpredictability isn't just about how complex things get? What if it's a fundamental rule of the universe, woven right into the fabric of reality itself? Well, to understand that, we have to go from the world we see to the unseen world of the quantum.
Now, before we go any further, it's really important to get this. There are two kinds of random. In our everyday world, randomness is just about ignorance. A coin flip feels random because we don't know the exact force, the spin, the air currents. If we knew all that, we could predict it. But in the quantum world, it's a completely different beast. The randomness is fundamental. The information about the outcome literally does not exist until the very moment you measure it. And this brings us to our second huge idea, quantum indeterminacy. This is the principle that tells us the universe, at its very core, is built on a foundation of maybes. So, put simply, quantum indeterminacy means that a particle, like an electron, doesn't have a definite property like its spin before we go and measure it. It just exists in this weird haze of possibilities. And this isn't because our measuring tools aren't good enough. It's a core feature of how reality actually works. Let's make this real. Imagine we measure an electron's spin in one direction. Let's call it sideways, and we get a definite result. Great, we know everything we can possibly know about that property. But here's the crazy part. If we then try to measure its spin in another direction, say up and down, quantum mechanics tells us the outcome will be completely random. A coin toss. A 50% chance we'll get up and a 50% chance we'll get down.
Now, this idea was so bizarre, so strange, that it led Einstein and his colleagues to ask this really profound question back in 1935. They basically argued that if this randomness was real, it had to mean that quantum mechanics was an incomplete theory, that there must be some hidden variables that we just couldn't see yet.
So where does all this leave us? Well, we have these two powerful theories. One gives us a map for sudden change in the world we can see, and the other reveals a fundamental uncertainty in the world we can't. And together they paint a picture of a universe that is way less certain and clockwork-like than we ever imagined.
And this is what's truly mind-blowing. Look at how these patterns echo across completely different scales. On the left, there's our cusp model for the dog's behavior, and on the right, that's a hysteresis cycle that describes how a magnet behaves. It's the same shape, the same underlying mathematical pattern for a sudden jump. It's a universal language for tipping points.
So, at the end of the day, we have these two incredible, complementary tools for dealing with an unpredictable world. Catastrophe theory gives us a map of the landscape. It shows us where the cliffs are, even if it can't tell us exactly when we'll fall off. But then quantum indeterminacy goes even deeper, revealing that the territory itself, the very ground beneath our feet, is fundamentally built on probability.
And that, I think, is the real takeaway here. The goal of science isn't always to get rid of uncertainty and give us perfect predictions. Sometimes its most powerful gift is giving us a clear, elegant, and powerful language to describe the nature of uncertainty itself.
Which kind of leaves us with one final big thought to chew on. If the smallest pieces of our world run on pure chance, and the complex systems built on top of them are prone to these sudden, unpredictable leaps, then what does it even mean to predict the future? Maybe the best we can do is not to know what will happen, but to beautifully understand the shape of everything that could.